Hello, good morning. Myself, Dr. Shaila Dinkarapte. Today, we'll move on to the linear filtering using FFT. That is, we'll deal with fast convolution algorithms. Firstly, let us see what is linear filtering. So, suppose we have some speech signal, which is, say, some lecture or some talk by some renowned person, and I want to filter it. I want to filter the audio. Say, I want to do low pass filtering. Then this lecture is running for, let us say, 1 hour. So there will be 1 hour into sampling frequency, so many samples. So the number of samples are very, very large. Now, when number is very large and when we are filtering, we'll have to use those many samples convolved with the impulse response of the filter, right? So it will be a huge number that we need to process, and we want to do it, say, real time. If we want to do it real time, we cannot process all samples at once. So what we do is we take few samples and go on processing the set of samples one after the other. Now in this case, this linear convolution, basically it is linear filtering, which is a convolution of impulse response of the filter with the signal that we want to filter. Let us say some talk. Now, convolution is computationally very costly. So, what we want to do, we want to somehow avoid convolution. We want to convert it into, say, multiplication, which is easy to compute. So, we can use DFT. The DFT is convert convolution operation into the multiplication. So if we have signal convolved with impulse response of the filter, after we take the DFT, it will be multiplication of the two DFTs, multiplication of the DFT of the signal and multiplication of the DFT of the impulse response. After multiplication, of course, we have to take inverse DFT. Now, we can use the FFT algorithm that we have studied that will reduce the computations involved in DFT. So what we can do is we can make use of DFT for converting convolution into multiplication, and then we'll have to use FFT for computation of DFT. Now we need to convert linear convolution to a circular convolution and then use FFT for computation of circular convolution, because FFT, when we are using, the actual operation that is carried out is circular convolution, and what we intend to calculate is a linear convolution. Right. So we'll have to convert the linear convolution into a circular convolution by appending extra zeros that we have seen previously, but I am just telling this again so that you can recollect the facts. Now, let us see how real-time filtering will be done. Now, when we are taking real-time filtering, we'll take the signal part by part, say chunk by chunk. So we can make use of the input buffer, which is of, say, suitable size, say to 128 samples or 256 samples or like that, which is 2 raised to some power. Why this is so? Because we want to use FFT. In order to acquire input data, as we want to make use of the FFT computation. So what we do is we acquire the input data. We have the input buffer. As the data is acquired, it will be put in the input buffer, and soon when the input buffer is full, the data will be transferred to the output buffer. And this output buffer data will be utilized for the computation of DFT and then convolution and the multiplication, whatever you want to do. And then when the input buffer is again full, again the data will be transferred to the output buffer. So data will be sampled um, with suitable size buffer, say either 128 or 256 or like that. And the data will be uh, acquired, and the previous data will be processed simultaneously, right? So when the input buffer is full, transfer the data to the next buffer from where the data will be taken for processing. Now use the data from the second buffer for filtering, and in the meantime, let the input buffer be used for grabbing the next further samples. So allowing the filtering operation to be completed before the input buffer is full again. That is a requirement because unless the operation is completed, we cannot transfer again the data from the input buffer to the output buffer. So this will be termed as real-time filtering, real-time processing. Now, when we want to do fast filtering, we'll have to use fast convolution algorithms. Now, just consider the problem that we can have. See, when we are having, say, n number of samples in the data and m number of samples in the filter, then the linearly convolved sequence will have n plus m minus 1. In this case, I am writing L plus m minus 1. L is the size of the data, m is the size of the filter. Then the linearly convolved sequence will have the number of samples equal to L plus m minus 1. That is, we will have to utilize more number of samples for the convolution, right? Now, when I take the input data, which is a large number, and if I divide it into small chunks, when I divide, the convolution of that segment of length L with the impulse response with with the length equal to m will generate L plus m minus 1, L plus m minus 1 samples. So for every chunk, every data segment, it will generate L plus m minus 1 samples. And we have seen when we studied DFT that the number of you can say DFT coefficients we are using will have to be greater than or equal to the number of actual samples in the signal when we take DFT. So in that case, otherwise if it is not done, then there will be what is called as aliasing. So if we want to avoid aliasing effect, we will have to see that the number of samples in the DFT will have to be greater than the number of samples in the data. That means in this particular case, the number of samples should be L plus m minus 1. Otherwise, there will be aliasing. Now, these algorithms that we are going to study are so designed that there will be correct number of samples obtained in the output and there will be no aliasing. Right. So let us study these algorithms. First algorithm is overlap and add. This is a block schematic for the overlap add algorithm. What we are supposed to do? This is a data sequence of length m plus L plus m minus 1. Filter impulse response will have length m plus L plus m minus 1. That is what we will do is L is the number of points in the data sequence, m is the number of points in the impulse response, but what we will do is here we will add L minus 1 samples as zeros, extra zero, sorry, m minus 1 as extra zeros, and here we'll add L minus 1 extra zeros so that both will have the length of L plus m minus 1. Then what we do, we take FFT of the data sequence, FFT of the impulse response of the filter. Then we multiply the two because the convolution is converted into multiplication when we take FFT. And after multiplication, we'll have to again take inverse FFT back so that we are again in time domain. And what we obtain is the circularly convolved output. Is that right? So this will continue for every data segment of length capital L. We will do this process and we will obtain the circularly convolved output. So this is a basic process that we will be using for FFT. Now, what is the algorithm for overlap and add? Let us go and see. Algorithm for fast filtering, that is overlap and add. So what we do, take the L samples of the data sequence, append m minus 1 extra zeros to this block of data so that its length is L plus m minus 1, as I told you. Append L extra zeros, L minus 1 extra zeros to the impulse response of the filter. So both these should have the length of L plus m minus 1, and then convolve the two sequences circularly using FFT. And then we will get the L plus m minus 1 points in the output. Next, what we do, repeat steps 1 to 3 for all the blocks. So if there are number of data blocks, say hundreds of blocks are there, we'll have to repeat this process for all hundreds of blocks. Note that if the last block is of shorter length, extra zeros will have to be appended. The next step is accumulate the result by adding the overlapped samples of the convolved output For successive blocks as shown in figure 21, I will show this figure 21. We are adding the overlap samples of the result, hence the name of the algorithm is overlap and add algorithm. Now in case of linear convolution, as the length of the output sequence is greater than the input data sequence, it is L plus M minus 1, whereas the data sequence length is just L. The output in the overlapping area of the output is contributed from the successive data blocks, right? So that is why we have to add up. Now just see this algorithm, overlap and add algorithm in detail. So this is the input data segmented into blocks of length L. So this is every block of length L that we have shown. Now we take this block of length L, append M minus 1 0, take again second block, again add M minus 1 0, so that the length becomes L plus M minus 1. Then we have the filter which is of length capital M. We'll have to append capital L minus 1 zeros to it, so that the length of the filter also becomes L plus M minus 1. And after you will carry out the FFT multiplication and then inverse FFT, we get this result. Now this is the result for the first block, this is the result for the second block, third block, and so on. Now how we are supposed to combine the result now? This is the output of the first block. So what we do, these m minus 1 extra zeros, those we have appended. So take last m minus 1 points in the first segment result and take first m minus 1 points in the second segment result and add up the two. Similarly, here m minus 1 points will be added, and after we add, we get the final result, which is the correct result. Let us take one example and see how it works. So let us, we are considering the input sequence as 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 15 samples I have considered, but deliberately I have considered 1, 2, 3, 4, 5, so that I will be making each segment of length 5, and the convolution result will be same for all because they are same segments. HN is 3, 2, 1, 1. So whatever the sample we have considered, samples we have considered. Now this we are considering capital L is equal to 5. So I will take 1, 2, 3, 4, 5. Then what I will do? I will append extra zeros, m minus 1 0. That is, in this case, capital M is 4. So I will append 3 zeros, right? Then I take the next segment, again append 3 zeros. So I generate these sequences. And then when I convolve it with the impulse response of the filter, I get some result. Now these are the 8 points in the result, because 5 is the data samples and 3 zeros are appended, so that the length of the sequence now becomes 8. Why I have chosen 8? Because 8 is 2 raised to 3, so I can use FFT computation. Now the result here is 3, 8, 14, 21, 28, and the extra sample that I am getting is 17, 9, 5. For the second sequence, second block, the result is 3, 8, 14. For the second block, the result is 3, 8, 14, 21, 28, 17, 9, and 5. So in this case, you will find that 17, 9, and 5 is overlapping with this 3, 8, 14. So here we will add the result. So 17 plus 3, 20, 9 plus 8, 17, and 5 plus 14 becomes 19. Again, we take further samples. Again, this 17, 9, 5 overlaps with these first samples. Again, we add that and we generate the result. So this is the result of the linear convolution with the actual data sequence. Now there is another algorithm called as overlap and save algorithm. Now in this case, what is happening is step 1. Again, we'll take L samples of the data sequence xn, append M minus 1 last samples from the first block at the start of the second block, and so on, so that the length of each block becomes L plus M minus 1. For the first block, there is no previous block, so we append zeros at the start. So for the first block, we append zeros at the start. And for the next block, we append the last points of the first block as the first points in the second block. So append L minus 1 extra zeros to the impulse response of the filter. This is the process is the same. Compute the two sequences circularly using FFT, and then repeat steps 1 to 3 for all the blocks. After it is repeated, we accumulate the result by appending samples of the convolved output for successive blocks. What we do is in this case, for how we combine, we discard first m minus 1 samples from every block. That is why it is called as overlap and save. First m minus samples will be discarded. We overlap the input data samples and save the rest of the non-overlapping result samples. And the algorithm is called as overlap and save algorithm. Now just see here. This is first L samples block. I append m minus 1 zeros at the start. For the second block, these are the m minus 1, these are the L samples. I append m minus 1 points from the previous segment, which are the last points. Now these become the first points in the next segment. Now, how the result is combined. This is the convolved output for the first segment. This is the convolved output for the second segment, convolved output for the third segment. Now, how I go about combining the result? What I do is I first discard these m minus 1 samples and append it at the end. Now here I will take L samples, then again discard these m minus 1 points, take further m samples, discard these m minus 1 points, take capital L samples, but these m minus 1 samples, these are not directly discarded, these are appended at the end of this particular sequence to get the result. So here is the example. Again, I am considering same sequence 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. HN is again 3, 2, 1, 1. So what I do is, how I consider this sequence? I will consider 1, 2, 3, 4, 5 as the signal values, and first m minus 1, that is 3 zeros, will be appended at the start. Now in the second case, 1, 2, 3, 4, 5 will be there, and last 3, 4, 5 will be appended at the start. Same thing will happen for the next blocks. And when I take the output, this is the output 17, 9, 5, 3, 8, 14, 21, 28. This is for the second block, this is for the third block. Now what we do? We discard m minus 1 samples here, discard m minus 1 samples here also. Take these samples. So see, 17, 9 and 5. I'll take all further samples. 3, 8, 14, 21, 28. Then discard first three samples here. Again start with 20, 17, 19, 21, 28. Again discard first three samples here. Then I'll have 20, 17, 19, 21, 28. And these last samples 17, 9, 5 will be appended at the end. So this is how again we are getting the same result for the convolved output. These are the two algorithms which automatically avoid what is called as aliasing and give us the result of convolution with less computational complexity. Thank you.